parametric surfaces. So this is our next topic. So just a very quick review of parametric curves, which was way back in a few chapters ago, right? Chapter 12, I believe. So you have this interval here of, let's say, from A to B. Right, so that's our t interval. And the mapping R maps that interval to a curve, right? This yellow curve over here. And if you fix a particular point, say t0, on the interval, that's a particular, if t represents time, right, then t0 is a particular time. You're at this particular location, this little purple dot over here, right? And so we're thinking about r of t0 as a vector from the origin. So this is the origin over here, right, to that point on the curve, right? And so different points on the curve will give you different times will give you different points on the curve here, right? Right. And of course, the derivative of r is your tangent vector, right? It's your velocity vector. So this represents the velocity, but we think of it, especially if we normalize it, it becomes a unit vector in the tangential direction. Right? Okay, so now we have parametric surfaces. So obviously for a two-dimensional surface, we need two parameters, u and v. So those are just the generic parameters, right? They don't have to be x and y, although that's one possibility. But just think of u and v as just two parameters, right? Just like t was a single parameter for a curve, for a one-dimensional curve, right? For a two-dimensional surface, we need two parameters. So we're going to use u and v because that's what the book uses, right? And, right, so if we pick a particular point, let's say u0 and v0 here, right? So that'll correspond to a particular point on the surface, right? Now remember, this surface is in 3 dimensions, so we have the usual coordinate system here, x, y, z, right? So we have our origin here, so that'll be 0. So, right, so R then maps, right, these two parameters, u0 and v0, to this particular point on the surface. So this will be the vector R evaluated at u0, v0. Make sense? Right, so let's not even distinguish between the, the vector and the point. I mean, obviously there's a difference between a vector and a point. I've discussed that many times. But yeah, we're just going to think about this as a point here now, right? Yeah, so so that's the location of the point. Again, it's some vector starting at the origin, but we're not going to, right? I don't want that vector to interfere with the other lines on the surface here, or the contours of the surface. In particular, right, if we fix u0 and we just think about all the other points, right, on that vertical line, one of which is u0, v0. So maybe I should emphasize that this point here, right, is u0, v0 in the uv plane. Right. So all those other points get mapped to, let's say, all of these points here on the surface. Or you can have, let's say, points of constant v, so let's say v0, and those would get mapped to all these points along that curve here, right? Okay, so yeah, at the intersection of those 2 points, the 2 lines, the green line and the red line, right, on the UV plane, you have your u0, v0, you have your point. And then at the intersection of the red curve and the green curve here, you have your your point, but again, it's three components, right? Three coordinates, right? So x evaluated at u0 and v0, y evaluated at u0 and v0, and z evaluated at u0 and v0. Right? So it's a vector. Same thing with it for a curve, of course, you had your three components. We just called them x, y, and z, but those only depended on one parameter, the t, right? The t0. Okay, so yes, so three components, x, y, and z, because this is a surface in space. And just like for a curve, this could have been a curve in space. I know we're thinking of it as a curve in the plane, but pretend it's a curve in space, right? For a surface, though, you have to have a surface in space. You can have a surface in 2 dimensions, but then it's just a plane. Right? Okay. Right. So again, I just want to emphasize that, right, we're thinking about this purple thing as the vector, and I can draw the vector again here, right, to that point. But if you want the coordinates of that point, then it's just, again, x of u0, v0, y of u0, v0, and z evaluated at u0 and v0. Yep. Right. And a different point, I'm running out of colors here, but I'll use blue, a different point in the UV plane, right? So say u1, v1, will just give you a different point on the surface here. So this will be r evaluated at u1, v1. Okay? So yeah, different points in the UV plane give you different points on the surface. All right. Now I want to talk about the tangent vectors, right? So if we have this red curve, and I take, let's say, the partial derivative of r as a vector with respect to, in this case, constant v, right? So with respect to u, because u varies along the red curve, along the red line here, right? Yeah, we get a tangent vector. So something like this, right? And then along the green line with constant u0, right, we get a tangent vector, maybe one that looks like this. So this will be the partial of r with respect to v. So v varies, but u is constant, right? Right. And I think, we should emphasize that this is, right, v0 is constant here, because it's only varying with respect to, right, with respect to u. So v0 constant. And for this partial derivative with respect to v, it's the u0 that's constant. Right? Right. So these two vectors then, the red one and the green one here, they span a plane. And we can think of that plane as the tangent plane to the surface. Right, in much the same way that, right, when you take the derivative of r on the curve here, you get a tangent vector to the curve. But for a surface, you need two tangent vectors to get a plane, right, to span a plane. And so how would we get the equation of the plane? Well, what do we need for the equation of a plane, right? We need a point, right? And we have that. That's the x0, y0, z0, right? So yeah, I'll just abbreviate this as x0, y0, z0. Right. So that's the point, and we need what else? We need not a tangent vector, because there's many of those. Right? We need a normal vector. So we'll use this vector. Oh, see, I'm running into the curve here. How about if I do it this way? Is that sort of perpendicular, right? So it's perpendicular to the red vector here, the u partial of r, and it's perpendicular to the green vector here. That's the v partial of r. So how do we get our normal vector n? Right, just take the cross product, right, because it's going to be perpendicular to both vectors, or I should say orthogonal to both vectors. So partial of r with respect to u, right, cross partial of r with respect to v. Okay, or, you can just do subscripts, right, r subscript u cross r subscript v. Right, because these subscripts mean take the partial derivative with respect to that variable. Right. Yeah, and I think we're doing it in that order, right? Right-hand rule. If you want a vector going the other way, which is also perpendicular to the plane, right? It's also a normal vector. We'll just call it negative n. And you can get that just by reversing the product here, right? The cross product. So this is partial of r with respect to v, cross partial of r with respect to u, right? Because remember that the cross product is anti-commutative. So you get a minus sign when you change the order, right? And so, yeah, you basically have to choose between which normal vector you want, right? So a choice of one of these normal vectors, when you choose which one of these vectors you want, the positive or the negative, right, we call that a choice of orientation. Right, and we'll talk about this a little later, but an orientation to a surface just means the surface has, right, two parts to it. You have the top of the surface, right, and then you have the bottom of the surface. So which do you want, the top or the bottom, right? If you want the normal vector pointing upward, right, you can say that's a positive orientation. And if you want the normal vector pointing downward, you can call that a negative orientation. Right? So yeah, we'll get into more detail later. But yes, the surfaces that we want to describe here all have, a top and a bottom. Or if it's not clear, like let's say you have the surface of a sphere, right? Now it depends on where you are on the sphere. If you're at the North Pole, right, there's a top, and then the inside of the sphere is the bottom, right? So that would be pointing this way. But if you're at the South Pole, it's the exact opposite, right? You're pointing outward, right, which would be the going up, and then downward would be going down. It would be going in. So for a closed surface like a sphere, we don't use top and bottom, right, or up and down. We use, inside and outside. So this is the outside, and then we have the vectors pointing inside or inward. Yeah, so I should say outward or inward. Okay, so yeah, so we'll get to that again a little bit later. Right. For now, we'll just take an example of a surface that you're hopefully familiar with by now. And that's a paraboloid. So z, as a function of x and y, is just x squared plus y squared, right? So that's the usual paraboloid here. Right. And then these are the other curves here, one going around the other way. So this is a surface, right? And of course we think of it as a function of two variables, and not all surfaces can be thought of as a function of two variables. But in the special case where you do have a function of two variables like this, right, one way to parameterize the surface, right, is to just pick u and v to be x and y respectively. So pick u to be x and v to be y, right? So in that case, right, our vector x, y, and z will just be the vector u, v, and remember what z is. Oh, that's a weird looking v. There's the v. Z is just x squared plus y squared. but we can't use x and y anymore. We have to use u and v sort of generically. So u squared plus v squared instead of x squared plus y squared, right? So we're just switching from x and y to u and v, right? I mean, you know, if you want to keep it as x and y, that's fine too. Yeah, plus y squared, right? And then your vector will just be a function of x and y instead of u and v. Okay. So again, I would only do that when you're talking about a curve where the uv plane just happens to be the xy plane. So each point on the xy plane will then correspond to a point on the paraboloid, right, in this way here, right, using this formula here. Makes sense? So yeah, so I generally would not use x and y as your parameters, right? Right. In the same way that for a curve, of course, right, you can represent a curve, like let's say you just have a parabola, right? It would be t squared. But here, x is t, so we could have just used x as our parameter and just use x squared. So there's nothing wrong with that. It's just that usually we like to switch to a different variable, to a different parameter t, because in most cases, right, t will not just be x or y. It'll be some very complicated function of x and y, right, like inverse sine or inverse cosine. So yeah, right. So for the same reason, we're usually not going to use x and y as our parameters. All right, so that's one way to parameterize the paraboloid, but there's probably a better way, right? And here's another way to do it, right? So we're going to use our UV plane as usual here, but now, right, instead of u and v being x and y, we're going to think of u as, let's say, the distance from the z-axis. So here's the z-axis here, right? So in this case, u would be r, right? So I'll put in the x and y axes too, right? And then v would be the angle theta, right? So we're basically using polar coordinates here, right? R and theta. And so here's the idea, right? For a particular r, for a particular distance here, let me use a different color. So I'll use light blue here. Right. For a particular, let's say r0, you're at a particular distance from the origin, right? So you're somewhere along this little circle here, right? So on the surface then, you go up to the surface and you'll be on, say, this circle along the surface, right? On the other hand, if you pick a particular value of theta, right, which is a particular value of v, right? So your constant theta, it might be this angle here, right? And so on the surface, if you go up to the surface, it'll be this curve here, right? Makes sense. And then the intersection of those two lines here, the blue and the red, give you, oh, I should use yellow here, give you a point, and that point will be this on the surface, right? Right. So, yep, so we're thinking about this in terms of r and theta. We know what x is, right? X is just r cosine theta. Y is r sine theta. And now we just have to find z, right? What's z going to be? Yeah, that's the curve, forget that, right? So it's the surface, right? The surface is z is equal to x squared plus y squared. But you remember that x squared plus y squared is r squared. So in cylindrical coordinates, or yeah, cylindrical coordinates, the surface would be z equals r squared. So z is just r squared. We can cut that off there. So, yep. But remember, we want to switch to u and v. So this will be r as a function of u and v. So we're going to have u cosine of v, u sine of v, and then, sorry, u squared, not v squared. right, v is the angle, u is the radial distance, right? So this is just a different parameterization of the same paraboloid, right? It represents the same surface, z is equal to x squared plus y squared, as this, right? But in some sense, this is probably more useful because it tells you, essentially where you are on the paraboloid, right? The u gives you the height above the xy plane, and the v, the angle, tells you where you are along that circle, right? What angle with respect to, right? So this is getting a little bit sloppy here, but yeah, this angle here, right? V, which is theta, it's just the angle with respect to the x-axis, right? So that fixes a location on the paraboloid. Okay. So two different parameterizations of the same paraboloid, right? And this is nothing new, right? Parameterizations are not unique, right? In the same way that you can represent a curve, let's say the upper half circle, you can represent that parametrically. Let's say it's the unit circle, right? You can solve for y and just let t be x. So this is the square root of 1 minus x squared. So your parameterization, right, could just be t, and then the square root of 1 minus t squared. Right. But not very useful, right? Typically when you think of a circle, you like to think in terms of, right, sine and cosine. So a more useful parameterization for the upper half of the circle is to say that, right, that t is theta here, and this will be cosine of t, sine of t. Okay? Oh, and that also brings up the idea, well, if you're only using the top half of the circle, right, then t only goes from, right, say 0 to pi. If you want to go over the whole circle, you would go 0 to 2 pi, right? But for the half circle, it's just 0 to pi. Okay. For this parameterization, well, right, x would have to be between 0 and 1, so t would be between 0 and negative 1 and 1. Sorry, not 0 and 1, negative 1 and 1. Yeah. Unit circle, radius is 1. Right. So going back up here, we should really specify what u and v can be, right? So in this case here, x and y could be anything, right? So u and v can be any real number from negative infinity to positive infinity, right? Remember, this is the infinite paraboloid. It goes up forever, let's say. But for this parameterization here, the second one, right, remember, it's not x and y anymore. It's u is the distance, so distance is going to be positive, right? So remember, r is greater than or equal to 0, so u should be greater than or equal to 0. And if you go all the way around 0 to 2 pi, you have the entire paraboloid. There's no reason to go around more than once, right? So v should be somewhere between 0 and 2 pi. Okay. Yeah. Again, if you don't say that, you're assuming that it's the biggest possible range, right? So if you only want a part of the paraboloid, let's say half of it, then, you can go from v equals 0 to v equals pi, from 0 to pi, right? And that means you're cutting the paraboloid in half vertically, right? So something like this, right, where this is cut off vertically here, right? And then this would be the other surface. So yep, so you can always do that. You can always restrict your variables to whatever portion of the surface you want, right? Right. For example, if you want to cut off the paraboloid, and instead of making it an infinite paraboloid, get rid of the arrows here. I used the wrong color. There we go. And let's say we want the top of the paraboloid here to be this surface at a particular z. let's say z is 10, right? So if we want that to be the top of the paraboloid, how would that affect our u and v? Well, again, if we want the entire paraboloid going all the way around, v would still be going from 0 to 2 pi. Right? But since z is 10 here, right, r would be restricted. Remember, z is r squared. So if that's equal to 10, r would be the square root of 10. Right? So u, which is r, would vary between 0 and square root of 10. So that would give you the finite paraboloid where this is the top of it and it doesn't go, upwards forever. Make sense? Okay. Okay, so we can do the same thing with the cone. Z equals square root of x squared plus y squared. Or maybe let's make it more interesting. How about z equals 2 square root of x squared plus y squared? So it's a little bit steeper here. Right? So the cone might look like this. Right. And yeah, let's make it a finite cone so it doesn't go up forever. Oh, and it's only half the cone, right? We're not worried about the bottom half here. If you want the bottom half, that would be z equals negative 2 square root of x squared plus y squared, right? So yeah, we can include that if we want, but I think in this case we'll just include the top half of the cone. And let's suppose that the top surface here, right, is going to be z equals, let's say 6, right? Right. So one way to express, one parameterization, I should say, to express the cone is just to use u as x, v as y, right? And then the parameterization would just be u, v, and then 2 times the square root of u squared plus v squared. Okay, so you can always do that for a surface that can be represented as a function. And this one can. Remember, if we wanted the bottom half of the cone, that would no longer be a function. It would be 2 functions, right, because it fails the vertical line test. Okay, so again, what are the bounds on u and v here? Well, let's see. Remember, z is 6 is the top part of the cone here. The surface up here, z equals 6. That's just the plane, right? That slices the cone at that level, right? Well, right. Remember, z is this. 2 times the square root of x squared plus y squared. Right, which is 6. So the square root of x squared plus y squared would be 3, or x squared plus y squared would just be 9. And all that means is that, right, the circle right below this here would have radius 3. Right? So this is r squared equals 9, or r equals 3. Okay, so yeah, so in other words, r would be between 0 and 3. Right, and theta would be between 0 and 2 pi, right? Unless you want to, again, cut the cone in half and not deal with, say, the left half of the cone, then you can go 0 to pi. But we want the entire cone here, right? Right. But remember, u and v is not r and theta at this point. It's x and y. So what are x and y doing? Well, yeah, so essentially you just have to do it this way, right? X squared plus y squared is less than or equal to 9. So in this case, u squared plus v squared would be less than or equal to 9. Okay. So yeah, that's a bit clumsy, right? So a better parameterization would be to switch to polar coordinates where, let's say, u is r again and v is theta. So in that case, u would be, well, right, x is r cosine theta, y is r sine theta. So x is u times cosine of v, and y is u times sine of v. And then z, well, remember, z is 2 square root of x squared plus y squared, which is just 2r, which is just 2 times u in this case, right? So now r goes from 0 to 3, or you can just say r is less than or equal to 3 because we know it's bigger than 0. But I'll make that explicit here. And then theta goes from 0 to 2 pi. Right. You don't have to include the 2 pi because that's the same as 0, but you know, it's fine if you want to include both, right? Right. But then you get repetition. You get one of these lines here. I think this one here would be repeated. Right. Yep. So each of these lines would be a different theta. And each of these circles, which I did in green here, would be a different different r. Right. Or a different z as well. Right. Yeah. Okay. So again, two good parameterizations for a cone. I would say this one's a little bit better, but that's just my opinion. I could be wrong. They're both valid parameterizations. I think the second one just turns out to be more useful. It's right, so no different than the paraboloid here. Two different parameterizations representing the same surface. Okay, so now we go on to the next example, which is a sphere. Perfectly good surface. We've talked about it many times. Very important surface, actually. And so this is the equation that you would use in rectangular coordinates, right? X squared plus y squared plus z squared is equal to the radius squared, right? So here, this capital R is just the radius, right? So capital R is just a constant, right? It's the constant radius for a sphere. Okay. So again, how would we represent that parametrically? Well, in this case, we really don't want to use u equals x and v equals y because you would need two different parameterizations, right? After all, then z would be the square root of, r squared minus x squared minus y squared, only for the top half of the sphere, right? And then minus for the bottom half. So to avoid that uncomfortable situation with the plus and the minus, we should use u and v as just the angles, right? So let's see, which one should we do? How about u is phi, phi, and v is theta, right? So all we need to do is get the x, y, and z components of this vector. And that just comes from spherical coordinates. Hopefully you remember x is rho, let's do it this way, sine phi, cosine of theta. Y is rho sine phi, sine of theta. And z was rho cosine of phi. Right. So these are on your formula sheet. That's just the standard, right, spherical coordinates. Right, and rho is the distance from the origin, but for a sphere, rho is a constant, right? It's just the radius. So yeah, so so this only depends on two angles, phi and theta. Right. So our vector then, I'll use I and j here instead, right? This is just going to be r sine of u cosine of v, r sine of u sine of v, and then z will be r times cosine of v. Oh, I said I, j, and k. I forgot that part. Sorry about that. All right, let's try it again, right? R sine u cosine v times I plus r times sine of u times sine of v times j plus r times cosine of v times k. So this is our perfectly good parameterization of the sphere, and it's not complete yet because we need to give the bounds on u and v. What part of the sphere do we want? Well, if we want the whole sphere, right, we want to go from the positive z-axis to the negative z-axis. So this is where phi is pi, right? The north pole is phi equals 0. So, right, phi is u, so u would vary between 0 and pi. And for theta, well, if we want to go all the way around the equator here, right, then that's the complete circle, 0 to 2 pi, right? So that means v, which is theta, would go from 0 to 2 pi. That gives us the parameterization of the sphere. Okay, remember, r is a constant here. This is constant rho, right? I mean, if we want a sphere with a different radius, we would use a different r, different rho, right? Yep. So this is probably just the most useful parameterization of the sphere, the one that we're going to use the most often, right? And you know, if you're confused about the phi and theta here, right? Again, we could have switched these. We could have made v equal to phi and r and u equal to theta. We would have gotten this sort of backwards here. But I think this is the one that I think this is the one in the book. So this is the one I'll stick with. Yeah. So a constant u is a constant phi, right? So a constant phi is a constant latitude, right? So different phis give different latitudes, right? So this is essentially the latitude, right? Except it isn't, right? Because if you're talking about the Earth, I need to move this down a little bit here. So I'm just going to copy it down here. Yeah, so if you're talking about the surface of the Earth, the equator is 0 degrees latitude, and then the North Pole would be 90 degrees, right? So the equator would be 0 degrees, the North Pole would be 90 degrees, and then the South Pole would be negative 90 degrees. But that's not what's happening with phi, right? With phi, the North Pole is 0 degrees, the equator is 90 degrees, right? And then the South Pole would be 180 degrees, or pi radians, right? So not the same as when you think of latitude for the Earth. So for that reason, sometimes this is called the colatitude, right? So yeah. What about v? V is theta, right? So those are lines of longitude, right? Or meridians. So these are longitude or meridians, if I can spell. Right. So yeah, this might be, if it's going through the x-axis, this might be, you know, v equals 0. This might be v equals, you know, pi over 2, right? Or 90 degrees, 100 degrees, and so on. So these are all different latitudes here. So to fix a point on the surface of the Earth, you only need two numbers, right? You need longitude and latitude. And that gives you a specific point on the surface of the sphere. Say this point right here would be for this specific longitude and then this specific latitude. I never gave an angle here, but let's say this is, I don't know, phi equals pi over 4. Okay. Right. So, yep, the idea is the mapping R, right, takes the points in the UV plane, right? And remember, U just goes from 0 to pi, but V goes from 0 to 2 pi, so you get this rectangle here. So every point on the rectangle corresponds to a point on the sphere, right? By this parameterization here, this R here, right? So this maps R as a vector, maps points, U and V, to a point or a vector from the origin. I should use a vector here. Right, so this is the vector R on the sphere, right? Okay. And maybe we should well, I don't want to get too deep into this, of course, but this is, right, this is not a one-to-one mapping, okay? Every point on the UV plane corresponds to a single point, not more than one point on the sphere, right? So you can't say that this point here corresponds to, say, this point and this point on the sphere. It only corresponds to one point on the sphere. But the reverse is not true, right? You can have a point on the sphere that corresponds to more than one point in the UV plane. Okay, and one example of that is the North Pole up here. So, right, the North Pole is phi equals 0. Let me try to get rid of this. It's not working. All right, close enough, right? Oh, this is not working. Hang on. Okay, I think I cleared that up. There was a little bit of an error there, but all right. So the North Pole, right? The North Pole here. So what does that correspond to? Well, that corresponds to phi equals 0, right? Or u equals 0. So u equals 0 is the v-axis, right? So this entire line here, this left boundary of the rectangle here, corresponds to only a single point, the North Pole. Right? So yeah, this v and u equals 0, this v, u equals 0, right? All these different v's here give you the same point, the North Pole. Right? And likewise, the South Pole down here corresponds to all these points, where phi is pi, or 180 degrees, right? Okay. Yeah. So what about constant v? Say v is 0. That's this red line here. That's going to be the prime meridian. That'll be this line right here, or this curve, this circle on the sphere. Right. So I used the wrong color. I should have used blue here, but it's a little late. So that's the prime meridian, right? Right. And if you want to go halfway around to the other side of the sphere, that would be this line here. Right. And what's this line where v is equal to 2 pi? Well, you're just back around to the same prime meridian again. So both this dark blue line and this light blue line down here correspond to the same points on the sphere. Okay, so yeah, not one-to-one, not one-to-one. But, right, to be fair, every point inside the rectangle, say this point here, corresponds to one and only one point on the sphere, and a point on the sphere that's not the North Pole or South Pole or the prime meridian would correspond to one and only one point in the UV plane. Make sense? Yeah. Right. Right. So yeah, these are different lines of longitude. Right. Longitude. And then the vertical lines here, right, these are lines of latitude, different latitude. So different circles on the sphere. All right, so that's the sphere. All right. So continuing with the example, suppose we just want to find a normal vector at the point on the sphere corresponding to phi is equal to pi over 3 and, oh, sorry, theta equals, yeah, I'm mixing my letters here. Theta is equal to 5 pi over 4. Yeah, so these are the angles. But just to be fair, right, u is going to be pi over 3 and v is going to be 5 pi over 4, right? That's how we designated u and v in the first place. Right. So what do we need for a normal vector, right? Well, we need to, actually, before we talk about the normal vector, what's the point on the on the sphere here, corresponding to this longitude and latitude. Okay, so in general, we have our parameterization, right? This is just the vector x of uv times I plus y of uv times j plus z of uv times k, right? And in this particular example, right, x is just capital R, so I keep messing it up, sine of u cosine of v, right, times I, and then y is going to be r times sine u sine v, and then z is going to be r times cosine of v, right? So yeah, so the actual point, right, as x, y, and z goes, we just plug those in, right? So r of pi over 3, 5 pi over 4. Well, let's see. So sine of pi over 3 is square root of 3 over 2. Oh, I forgot the r. Okay, we'll multiply by r. Cosine of v, cosine of 5 pi over 4 is... Wait, 5 pi over 4. Yeah, it's between 0 and 2 pi, so that's fine. Yeah, it's just negative square root of 2 over 2. So we'll do negative in front, square root of 2 over 2, and then times r, of course. And then y is going to be r times sine of u sine of v. So sine of u is still square root of 3 over 2, and then sine of 5 pi over 4 is going to be negative square root of 2 over 2, again times r. And then cosine of 5 pi over 4 is negative square root of 2 over 2, right, times r. So yeah, the r is a constant. It can come outside. But then, so this is the corresponding point. So yeah, x, y, and z are all negative here. So yep, negative square root of 6 over 4 for x, oh, times r. And then negative square root of 6 over 4 times r for y. And then negative square root of 2 over 2. Space issues. Too much space here. Okay. Negative square root of 2 over 2 times r. So that's the corresponding point, right? Again, that wasn't the question. We're looking for, right, the normal vector at that point. Well, right. So if you remember, the partial of r with respect to u, or r subscript u, is a tangent vector to the, well, to the sphere, but also to the tangent plane at this point. And so is the partial of r with respect to v, or r subscript v. That's another tangent vector. And so when you take the cross product, you can get your normal vector. Okay, so before we take the cross product, we have to find the partial derivatives, right? And luckily, right above it, we have the parameterization. So just take the partial of x with respect to u. Or maybe let's just write this out in its detail here. This is partial of x with respect to u times I, plus partial of y with respect to u times j, plus partial of z with sorry, z is not a vector. Partial of z with respect to u times k. And then the same thing but for v, right? So partial of x with respect to v times I, plus partial of y with respect to v times j, plus partial of z with respect to v times k. Right. So without further ado, let's just write down these vectors here. So this is going to be r cosine of u cosine of v times I, plus r, let's factor out the r. It's a constant, right? Yeah, cosine of u sine of v times j. And then, well, this doesn't depend on u, so this is 0 times k, right? And then for the v partial of r is the x partial, the v partial of x. So that's going to be negative sine of u sine of v times I. and then plus, yeah, the derivative of sine of v is cosine v, so sine of u, sine of v, no, cosine of v, getting confused here, times j, and now we have negative sine of v times k, right, all times r. So, yep, now we just take the cross product, right? So imagine your determinant, I, j, and k here. Take the determinant of all that. And so for the I component, what are we going to get? We're going to get, first of all, r times r is r squared. So let's factor out the r squared. Yeah, so negative cosine u sine v squared. So negative cosine of u and then sine squared of v. Right, and that'll be times I. And then for the j component, oh yeah, because this is 0 times sine u cosine v, right? And then for the j component, we're going to get positive. Yeah, because we're doing negative this, right? So this is going to be a positive cosine u sine v cosine v times j. I think that's right. So that is a sine v there. Okay. And then for k, oh, it's going to be 2 of these, right? It's going to be positive cosine u sine u cosine squared v. So I'll do sine u cosine squared v. And then minus a negative, so positive sine u cosine u sine squared v. All times k. Right, so kind of a mess here. However, if you notice in here, we can factor out the sine of u, cosine of u, and then we get cosine squared v plus sine squared v, which is 1. So this is really just sine u cosine u. So we can simplify this pretty drastically here. And maybe I'll go back to bracket notation then, right? So this will be negative cosine u sine squared v, and then cosine u sine u v cosine v, and then sine u cosine u, all times r squared. And for some reason I can't help but think I made a mistake here, so let me check this. Yeah. So wait a minute. V is theta. This is not cosine theta. This should have been a u up here, cosine of u. So yeah, I got the parameterization wrong. This is cosine of u, not cosine of v. So let's see, hopefully an easy fix here. It's just the last component. The last component, yeah, the 0 here is wrong. This should have been negative sine of u. And then the second one should have been the 0 here. All right, is that clear enough? Yep, so this is negative sine u times k. All right. And then for the second partial derivative, I think the first 2 components are fine. And then we get 0 for the third component here. So let's see if I can erase all this. And just put a 0k here. Oops. Yeah. Okay. So this is plus 0k. Yeah. All right. So that also affects the cross product, though. So the first cross product would have been negative sine squared of u cosine v. Boy, so that, okay, so, right, so this is completely wrong here. Okay, so I think I might as well just start over here and do it properly. So for the determinant, we have 0 minus a negative, so that's positive sine squared of u times cosine of v times I, right? And then the second component will be the y, so that'll be negative times a negative, so that'll be positive sine squared of u, but now it's sine of v times j. Oh, sorry, that should be a plus, not a comma. All right, and then the third component will be this minus this, so sine u cosine squared v, oops, sine u, cosine of u, and then cosine squared of v. And then for the other diagonal, we get sine u, sine squared v. So again, cosine squared plus sine squared equals 1, but it should be the v, not the u here, right? Okay. So, yeah. So let me fix this one down here. Okay, so I think that's it. That looks better. It looks more symmetric to me anyways. All right, so that's a normal vector at any u and v. Our particular u and v was given as pi over 3, 5 pi over 4, right? So for our normal vector, specifically at the point where u is pi over 3 and v is 5 pi over 4, again, the r squared is just the radius. We can factor that out. So sine of pi over 3 is square root of 3 over 2, but when you square it, you get 3 over 4, times cosine of v. Cosine of 5 pi over 4 is, again, negative square root of 2 over 2. Right? And then sine squared of pi over 3, that's 3/4 again. Sine of 5 pi over 4 is also negative square root of 2 over 2. And then sine of u is square root of 3 over 2. Cosine of u is also, no, cosine of pi over 3 is 1/2, right? So times 1/2, no comma here. Okay, so that's the vector. Let's just multiply it all out. In fact, I'll include the r squared now, right? So this will just be negative 3 square root of 2 over 8. Negative 3 square root of 2 over 8. Oh, I forgot the r for the radius. I should have just made r1 for the unit sphere, but too late now. And then square root of 3 over 4 times r. Okay, so that's the particular unit vector at that particular point. So does that make sense? Yeah, so the z has a positive component because it's in the upper half of the sphere, the northern latitudes, right? Yeah, above the equator. Right, and I know that because phi is pi over 3, which is 60 degrees. Yeah, so that's somewhere here, right? That's somewhere in the northern latitudes. All right, makes sense. Right, so yeah, the normal vector will be pointing, slightly upward at around that point. It'll have a positive vertical component. But it's in such a location that the x and y is going to have a negative component. It'll be pointing outward in that way. All right, so that's a good example using the parameterization of the sphere. Okay, so here's another example. Very similar. Find the equation of the tangent plane to the cylinder x squared plus y squared equals 25. You should recognize that's a cylinder at the point 4, negative 3, 2. Okay, so yeah, we could have done that here too. Once you find the normal vector, right, and you have your point, your x, y, and z, way up here, you can find the equation of the tangent plane at that point, right? So this is your a, b, and c. This is your x0, y0, z0. Put it all together and you get the equation of a plane. Obviously, it's going to depend on r because it depends on the radius. But yeah, here this is a specific cylinder with radius 5. Well, maybe we should try to graph it here. Okay, so here's the xy plane. Oops, y is here, and then z is here. And so we're presuming this is the infinite cylinder. It goes on forever, both upwards and downwards. So z could be positive, z could be negative, right? And let's see. So x is 4, 1, 2, 3, 4, right about here, and y is negative 3. So we're talking about the point right here. And of course, z is, let's say, 1, 2, so it's up 2 spaces. That looks about right. So this point right here is the point 4, negative 3, 2, roughly speaking. Right. Yep. So these are the meridians, if you will, on the cylinder. Right. Okay, so we want the tangent plane there. So what do we need? Well, right, so we need a point. We have the point. That's given. We just need a normal vector, right? And, of course, you can find it by using the gradient here. That's not a big deal. The problem is, oh, actually, that is a problem because this is not a function of x and y, right? It's a vertical cylinder. So yeah, I don't think we can do it that way, which is probably why we haven't asked you for the tangent plane of a cylinder yet, at least not a vertical cylinder like this. If you have a horizontal cylinder, right, then you can think of it as two surfaces, the top and the bottom, plus the square root and minus the square root, right? All right. All right. So how do we get a normal vector? The same way we did for a sphere. We need to first parameterize the cylinder. And of course, we're not going to use x and y for u and v. We're going to use the usual. U is r, v is theta. Right, so this will just be the usual r cosine theta. Oh, here r is constant, right? R is 5. Right, so u is just 5. Right, so only v varies here, right? So this is going to be 5 times the cosine of v and 5 times the sine of v. And then z. Oh, yes. So u is not it can't be u here. R is a constant 5. We need a parameter for z, so that'll be my u, I guess. And now I wish I did it the other way. So, yeah, why don't we let u be theta and v will be z. So these are u's now, and v will be z. How's that? And that should be, obviously, a bracket instead of a parentheses. Okay, so I messed that up entirely here. Let's just rewrite it, right? So this will be 5 cosine of u I plus 5 times the sine of u j plus vk, right? So, yeah, u is theta and v is z. So that means u just goes from 0 to 2 pi as usual. And v could be any real number if it's the infinite cylinder. Right? We can always restrict that, say, from 0 to 5 if we want a cylinder of height 5. But in this case, it's the infinite cylinder, right? Okay. Right, so this is just expressing that x, right, is 5 times cosine of u, y is 5 times sine of u, and z, well, z is just v by definition. That's So we know the coordinates, right? 4, negative 3, 2. So if that's 5 cosine u and 5 sine of u and v, well, we know that v is 2, right? Because that's z. And we know cosine of u is 4 over 5. And we know that the sine of u is negative 3 over 5. So based on that, we can pretty much find what u is, right? It's going to be the arc cosine of 4/5. Wait, do we want that? Let's see. So x is positive, y is negative. Yep, that's right. So the arc cosine of 4/5. Oh, minus pi, right? Because the arc cosine of 4/5 will be in the wrong quadrant. It'll be up here. Right. So instead of doing that, maybe let's just do the arc sine of negative 3/5. Oh, that's not right either. Because that'll be a negative angle. Remember, theta goes from 0 to 2 pi. It shouldn't be negative. So, right, if this is the negative angle, you're going to have to go all the way around, so you're going to have to add 2 pi to that. So we can write it either way. Yep. Oh, minus pi, not plus pi. Oh, no, it is plus pi, right? It is plus pi. Because our cosine will be between pi over 2 and pi. We want to be between 3 pi over 2 and 2 pi. Okay, so it wasn't minus pi, it was plus pi. Sorry about that. Right, so either one of these will work. So that gives you the angle here, right? Anyways, the problem was to find the equation of the tangent plane. So what do we need? We need a normal vector, right? So we need the two partial derivatives of r. Let's get ru. Right? Remember, that's just notation for the partial of r with respect to u. And that'll be the vector negative 5 sine of u times I plus 5 cosine of u times j plus 0 times k, since v doesn't depend on u, right? And with respect to v, the partial of r with respect to v will just be 0i, right, plus 0j plus 1k. I'll put a 1 there. So for the normal vector, we just take the cross product, ru cross rv. And yep, so the I component will be 5 cosine of u minus 0. So 5 cosine of u, sorry, that's a 5. I'm mixing my i's notations here. So I'll stick with I, j, and k, right? So 5 cosine of u times I, and then plus 5, that is a 5, not an s, plus 5 sine of u times j, plus 0 times k. Yep, so the normal vector obviously will not have a vertical component because it's a cylinder, right? The normal vector points directly outward. We don't expect it to point upward or downward because that won't be perpendicular to the cylinder. Perpendicular to the cylinder is, right and left. But of course, if you're going along the circle, you get these outward pointing vectors here. Right. Anyways, yeah, so now we just plug in the numbers. So at the particular point, 4, negative 3, 2, well, all we need is the cosine of u, and the cosine of u is 4/5, right? So this is just going to be 5 times 4 over 5, right, times I, plus 5 times negative 3 over 5 times j, plus 0 times k. So this vector is just going to be 4, negative 3, 0. Right? Or if you prefer, 4i minus 3j. Right? Either way. Right. So that's what this little vector pointing outward here. Oh, right, we know it's pointing outward. I think it's pointing outward, right? If you look from the top down, right, if this is the z-axis here, What color? Oh, I did use yellow for the circle. Right. So if this is the cylinder going around the center here, and this is my usual x and y, right? X is positive, y is negative, so that's going to be, yep, this point over here will be the point 4, negative 3, 2. So of course, our vector pointing outward will also have components, 4, negative 3, but remember, there's no z component, so it's just z equals 0. So yeah, we could have guessed that, of course, just based on the fact that we could have moved this vector here and just moved it over here. It's pointing in the same direction. Right? It should be pointing radially outward. I know it's a little bit bent. Is that a little bit better? Yeah. Okay, so that's our normal vector. Oh, we wanted the equation of the plane, not the actual normal vector. All right, so a good review for tangent plane, right? We know the equation of the plane. Here it is one more time. Equals 0. So plug in your numbers. 4 times x minus 4, minus 3 times y minus 3, plus 0 times z minus 2. So we're going to get 4x minus 3y minus 16 minus, plus 9. Yep, negative 3 times, positive 3, right? Y minus y0 is y plus 3. So I was right the first time. It is negative 9, not positive 9, equals 0. Right? Or if you prefer, 4x minus 3y minus 25 equals 0. Let's try that again. There we go. So that's the equation of the tangent plane. Right? Yeah, it's a vertical tangent plane, right? It doesn't have a z because it's a vertical tangent plane. Just go straight up and down, right? If you look from above, the tangent plane would look like this, right? I know it's a tangent line, but you have to imagine the z, right, coming out at you here. So this is a plane coming out at you. Yeah, remember the z-axis is here, coming straight out of the screen. Okay, so again, more good examples. Okay, so now we can find the surface area, right, of a parametrized surface. So we have a smooth surface S, parametrized by R, right, R of u and v, the usual way, and it's defined on an open region R of the UV plane. And here we have to assume that every point of the surface corresponds to exactly one point of R, right, of point UV of R, right? In other words, that this function R, right, has to be 1 to 1. Okay. So with that in mind, and it usually is, again, if we're talking about like the sphere, we had issues with the North Pole and the South Pole and so on. But other than that, the surface area can be calculated as this quantity here, right? So it's the integral over all the little patches ds, right, over the surface S. But as a practical matter, what you do is you take the two partial derivatives of R with respect to u and with respect to v, take the cross product, right? And in fact, we did that already, right? That's just your normal vector. And then you take the magnitude of that vector, right? And then you integrate that quantity over the entire region R. Okay. So again, it's kind of a mysterious formula. It's like, where does that come from? So we'll do an example first, and then we'll see where this magnitude of RU cross RV comes from. Right. So how about the sphere? Right. Find the surface area of the sphere of radius R. And you probably know the answer already, I would hope. But we want to figure it out based on this formula here, right? And this is one we could have done in section, what is it, 14.5. And I don't think we did, right? What you had to do was take the square root of r squared minus x squared minus y squared, and that's your function of x and y, right? Of course, it's plus or minus, but we're going to just, because it has to be a function, we're just going to deal with the top half of the sphere. And then we could have done it by doing the usual square root of 1 plus, right, fx squared plus fy squared. You should have done this for homework. At least I hope this was somewhere in the homework. But if not, yeah, that's one way to get the surface area of a sphere. Of course, what you end up with here is 2 pi r squared, right? But remember, that's only for the top half. For the bottom half, you have to double it. So you get the usual formula, 4 pi r squared. Okay. So, all right, so spoiler alert, the surface area of a sphere is 4 pi r squared. Okay, but we're going to derive it based on this formula, not from 14.5. Okay, so first thing we need, of course, is the parameterization, and I'll just remind you of that. We've done it many times before. So yeah, we're going to leave the r on the outside because that's a constant radius. I'll use brackets again, right? So sine u cosine v, and then sine u sine v for the y component. And then I got this wrong last time, so let me make sure I get this right, right? U is phi, right? So there should be cosine of u, not cosine of v. That was my mistake before, right? So I'm glad I didn't make that again, right? And what do we need to do? Well, we need to take the partial derivatives, right? So remember what this stands for, right? This stands for the partial of r with respect to u. This denotes the partial of r with respect to v. So let's take both partial derivatives. First with respect, sorry, u is not a vector, r is the vector. Partial of r with respect to u, or more concisely, just ru. Right? And we did this already too, so I will just quickly remind you. Cosine of v, cosine of u, cosine of v, yikes. And then cosine of u, sine of v times sine of v, and then negative sine of u. Right. And then the v partial of r, or rv, again, capital R times negative sine u sine v, and then sine u cosine v. Sorry, that's a u. And then 0, because this does not depend on v here. Right. And we already took the cross product as well. That was our normal vector. I guess let's do it again. Doesn't hurt to practice. So this was what? This was sine squared of u cosine of v for the first component. The second component will be positive sine squared of u times sine of v. And then the third component was sine u times sine v. Nope. What was it? It was, yeah, sine u cosine v. No. Sine u cosine u. There we go, right? Because you get cosine squared v plus sine squared v is 1 for the rest of it. Okay. So there it is. Now all we need to do is take the magnitude, or the norm, of that vector. Right? So you're just going to get r. And then, well, it's going to be the square root of this squared plus this squared plus this squared. So let's work it all out, right? So sine squared squared is sine to the 4th u times cosine squared v plus sine to the 4th u times sine squared of v plus sine squared u cosine squared u. And that's a bit of a mess here, but it does simplify a little bit. If you notice, in the first two terms here, we have a constant, we have a common factor of sine to the fourth of u. So if we factor out sine to the fourth of u, that just multiplies cosine squared v plus sine squared v, which is 1. And I'm just copying everything else down. Right? So, yep, that helps a lot. Now we just get sine to the fourth of u plus sine squared of u cosine squared of u. And, well, we can factor out a common factor of sine squared of u. So we get sine squared of u plus cosine squared of u. And that's also equal to 1. Right? So taking the square root, you're just going to get r times sine of u. Yeah, if you're thinking absolute value, right, because it's the square root and sine of u could be negative, then there should be absolute value here. But remember, u is phi, and phi ranges from 0 to pi. And sine of u will just be from 0 to 1. Right? So it's not going to be negative, which means we don't need the absolute value here. It doesn't hurt to... Ooh, sorry about that. My apologies. I forgot to use my blackout tool. I did yellow for the whole thing. There we go. All right. There's probably an easier way to do that. To get rid of the absolute value. Okay, so that's it, right? This is the absolute value of Ru cross Rv. So now for the surface area, so back to surface area, we just have to integrate over the region R. We'll figure that out in a second, right? This was the magnitude of Ru cross Rv over the area of the region A, right? And so we're just integrating over, that's why the book uses A for the radius. So I shouldn't use R here, right? What should I use? How about D for domain? Or for, yeah, except it's not a disk, is it? So this is not an R. This has nothing to do with the radius. This R here is just the region in the UV plane. So D is the region of the UV plane, which is the usual region, right? U goes from 0 to pi, and V goes from 0 to 2 pi. Right? It's this rectangle. So I wanted to use R for rectangle. Right? If this is pi, this is 2 pi, right? This is U, this is V. So it's just this rectangle here. The same one we talked about earlier, right? Okay, yeah. So, okay, now I know why the book uses A for the radius. But we've used A for other things too, I guess. Acceleration, for example. All right, so I could have left it as R, just as long as you recognize it's not the same R as this, the radius of the sphere. All right, so yeah, this is just R sine of u, right? And then dA, of course, is just du dv, right? So if you're wondering, well, wait a minute, what about the Jacobian, right? This is the Jacobian, right? This takes care of all of that, right? So don't feel like you have to figure out the Jacobian here for the u and v coordinates, right? This is always going to be the case. It's just du dv. Okay, right? So it's not like, u du dv here, like you needed an r, right? After all, these are just angles. There's no r's, right? So, yeah. Right. Or if it helps, you can think of this as the integral of r times the sine of phi, right, d phi d theta. So, yeah, there is no dr, so there's no r dr, and so on. Right, and phi goes from 0 to pi, and theta goes from 0 to 2 pi. I should have saved that for later here. The r is a constant. That can come outside. And yeah, d is just, well, here it is one more time, right? U goes from 0 to pi, and v goes from 0 to 2 pi. And it's just sine of u du dv. But if you want to evaluate it using phi and theta, that's fine too. It's the same thing. Okay, so let's evaluate the inside integral first. Yep, so this is just the integral from 0 to 2 pi. The integral of sine is negative cosine from 0 to pi. And again, there's going to be a lot of negatives here, so because I always get that mixed up here, let's just do cosine of u from pi to 0. Right, and that's just 1 minus negative 1, right, which is, of course, 2. So we'll bring out the 2. And we still have one more integral to do. This is the trivial one. This is over theta, right? So you just get 2r times v evaluated between 0 and 2 pi. So 2r times 2 pi is 4 pi r. Which, of course, is wrong, right? It's 4 pi r squared. So what did I do wrong? This is right, this is right. Oh, yeah, in the determinant, this was r squared. I had it right earlier, but these are all r squareds. Yep, so r squared times sine of u. Right, so yeah, this is r squared here, r squared here, r squared here. Yeah. Everywhere you see an r, just replace it with r squared. I don't know why I didn't see that earlier, but I knew it had to be wrong because this is the surface area of a sphere. It's 4 pi r squared, right? If it was just 4 pi r, that would be a distance, not an area. So now the units are correct. 4 pi r squared is the surface area of a sphere, which, again, we knew that already. But this is one way to figure it out. And yes, be careful you don't make the same mistake I did, right? When you do the determinant here, you're doing r times r, right? So this has an r, this has an r, and so r times r is r squared. So I missed that. But in the end, you know, now it's correct. All right, so that's one example of finding surface area. I hesitate to do one more, but I feel like maybe I should, just to make up for that silly r squared mistake here. Okay, so this is one of my favorites. I think this is in the book too. We want to find the surface area of a torus. And it's given by this parameterization, right? So coming up with the parameterization isn't exactly easy. You know, it's just looking at a surface of a torus. So a torus is just a donut. So surface looks something like this, right? There's a hole in the donut here. So I hesitate to fill this in because it's just not going to look right, but it's the surface here, right? And then there's the hole in the middle. So roughly speaking, we get this by doing, think of it as a surface of revolution, right? This is the xy plane here. This is the z-axis. Again, the z-axis is up here, right? Should be vertical. I struggle with vertical lines. There we go, right? So, so this part of the torus is just a circle. And so we're just taking a circle here, and we're revolving it around the z-axis, right? So this is the surface of revolution of the circle revolved around the z-axis. Yeah, this is kind of hard to draw here, but this is the surface. So you'll have the same thing over here, and then moved around this way. Right. So this torus has a very big hole in the middle, maybe even bigger than a regular donut. Okay, so notice that u and v both go from 0 to 2 pi. And if that seems strange, because for the sphere, right, we only went from 0 to pi. So here, u and v are not just the usual phi and theta. Okay, so v is the angle. If this is the circle here, it's this angle in here. Okay, it's this, v is this angle here. I want to make sure that's right. And a and b, let's see, a has to be bigger than b. So a is the distance from, I'm running out of colors here. The origin to the center of this circle here, right? Roughly right here on inside the surface, right? So that's a. B is the radius of the little circle, right? So b is this radius in here. Okay. So now I think I see why, right, v has to go from 0 to 2 pi, because you're going all the way around the little circle here. You know, if you want to cut your donut in half, and by half I mean, you know, the wrong way, right, horizontally, so you have the top half of the donut and the bottom half of the donut, then v would be going from 0 to pi, because you only want the top half of the donut. But for the whole donut, yes, v goes from 0 to 2 pi. Okay, now what's u? U is going to be the angle. So here's the x-axis, here's the y-axis. We want to go all the way around the donut, right? So that's 0 to 2 pi as well. So essentially, u is the usual angle with respect to the x-axis. And I know I'm running into myself here. This z is in the wrong place. Yep, so this is the z-axis for the bottom figure, and this is the x-axis for the top figure here. There we go. Right. So yeah, so u also goes from 0 to 2 pi. Right. All right, so that maybe explains a little bit about the parameterization, right? And a has to be bigger than b, otherwise you don't get a hole. Right. So imagine a donut without a hole. Right. So you might have this, but there's no hole in the middle. Right. Right. In other words, you're revolving something like this around the z-axis. So, right. So you get a little pinch in the middle here, but it doesn't become a complete hole. So that's what would happen if a was less than b. Right. And so we don't want that here. We want, you know, if not a hole, then at least a tiny, you know, either a tiny hole or just where they come together here. Okay, so that should do it. So to find the surface area, we use the same formula for surface area. It's just the double integral over the region R of the norm, or the magnitude of the cross product of the two partial derivatives with respect to u and v. Right. And remember, this will always be just du dv here. Right. This will become the Jacobian, so to speak, for surface area. We don't call it that, but you know. All right. So what do we need? So we need to take the parameterization up here and take the two partial derivatives of that. So r with respect to u. Remember, partial of r with respect to u. So it's a vector, right? It has three components. So the first component with respect to u is sine of u. So, oh boy. All right, I'm gonna use the bracket notation here. I know I go back and forth, but you'll see why in a second, right? So this will be negative parentheses a plus b cosine v, and then sine of u, right? The second component of the vector here, the partial of y with respect to u, will just be positive a plus b cosine v times the cosine of u. And then the third component with respect to u, this will be 0, right? Yeah. Yeah, so we need a 0 here. All right, and then the partial with respect to v. Okay. So now the derivative with respect to v, so we keep the cosine of u, and this is going to be well, the derivative of a is 0. The derivative of b cosine v is negative b sine v times cosine of u. Right? And then same thing for the second term, right? Negative b sine v, but times sine of u. And then the derivative of b sine v is b cosine of v. So I think that's it. Now we need the cross product. So imagine this is the determinant again. This is your I, j, and k up here. Right. So the first diagonal is this. So we're going to get the vector again in component notation. So we're going to have a b. We're going to have cosine u cosine v times a plus b cosine v, and that's going to be a little confusing, but I think that's everything, right? And then minus 0 for the other diagonal. Oh, I put that in here, sorry. And then 0 times this minus this, so that's going to be a positive b times a plus b cosine v in parentheses, and then sine of u cosine of v. And then the third component is, oh, it's 2 terms, so it's going to be kind of a mess here. I think I'm going to run out of space also, so let's see if I can squeeze that in over here. So we definitely get a positive b times a plus b cosine v. So we have sine of u, so that's sine squared of u, times sine of v. Right. Going the other way, you have the cosine squared of v. Everything else is the same. No, cosine squared of u. Right. Everything else is the same, I think. Right. b times a plus b cosine v times the sine of v. Yep. All right. So this is nice because this ends up being 1, Pythagorean identity. And so I guess we'll just clean this up. We do have a common factor of b as well as a plus b cosine v. So all that can come outside. And we have inside, we have cosine u cosine v, sine u cosine v. And then we brought all this outside, so we just get sine of v here. Right. And then, yeah, sine squared plus cosine squared of u is just 1. All right. So that's the cross product. Now we need the magnitude. Right. Which is just going to be yeah, the square root of all this squared, right? So let's see, do we get this squared? No, because the r squared came from r times r here. Right, we might get a b squared eventually if we multiply this out. But right, this just becomes the common factor. So don't square this, but you're going to take the square root of cosine squared u, cosine squared v, plus sine squared u, cosine squared v, plus the sine squared of v. And I should save you the trouble that, right, this whole square root is just going to be 1. It's just 1. So all that's left is the b times a plus b cosine of v. I mean, you can work this out, right? You're going to factor out the cosine squared of v, and you get cosine squared u plus sine squared u. So that's 1. But then you get cosine squared v plus sine squared v, which is also 1. So sure enough, this is just b times a plus b cosine v, right, times the square root of 1, which is 1. And that v looks a little like a u, right? So in the end, we get ab plus b squared times the cosine of v. Make that a v. Right. Okay, so that's not the surface area, right? We still have to do the integral here. But this is the integrand. This is what we're integrating here. So back to area. It's just the double integral over r of the magnitude of ru cross rv, right, which is just this, again, du dv. Right. Now, what was r? What was the region here? Right, well, that was given to us, right? U and v both go from 0 to 2 pi. So we're doing, let's see, we're doing du first and then dv. U goes from 0 to 2 pi. And v goes from 0 to 2 pi as well. Right? Remember, this is not a sphere, so this is not the usual phi and theta. Okay, and the integrand is, well, ab plus b squared cosine of v. Right? So let's work this out. We'll do the inside integral first with respect to u. So we'll do the v later. Yeah, this is just a constant, so this is all times u. So why don't we bring out the constant here? Cosine of v, right? And then we just integrate from 0 to 2 pi of 1 du, which is, of course, just 2 pi. Now comes the hard part, I suppose. I mean, it's not that hard, but it's the v integral now, right? So ab is a constant, b squared is a constant, but we just have to integrate cosine of v, which is sine of v. So keep the 2 pi. So this is ab times v plus b squared times sine of v, right? And then we just evaluate this between v equals 0 and v equals 2 pi. So we get a times b times 2 pi, right? So 2 pi ab plus b squared times, well, the sine of 2 pi, but that's the same as the sine of 0, which is 0, right? So that's just 0. Oh, should I write it out? Yeah, so yeah, sine of 0 is 0, sine of 2 pi is 0, so this just ends up being 0. And then minus, ab times 0 is also 0, right? So there you go. 2 times 2 is 4. Pi times pi is pi squared times ab. Okay, so that is the surface area, right, of the donut. Or mathematically, we use the word torus. But a torus is just essentially just the shape of a donut in most cases. Okay. Yep, a times b. A and b are lengths, right? A and b are distances. So a times b is an area, right? So this will be in units of meters squared, or square inches, or square feet, or whatever your units are. Okay, yeah, so that's the surface area of this donut here. It's just 4 pi squared times AB. And, if A and B are 1, so you can think of that as the unit torus, right? Just revolve the unit circle around the x-axis. So you don't really even get a hole in that case. You get the pinch comes to a point here in the middle at the origin, but I would still say it's a donut. It's just a donut with a very, like a non-existent hole. So that would have area 4 pi squared, right, times 1. But in general, when a and b are not 1, you have the more general formula for the surface area of a torus. So yeah, a lengthy calculation to be exact, because you got to do the partial derivatives, then the cross product of those, and then the magnitude of those, and it's a pain. But, you know, this is one way to do it. And probably one of the easier ways, I think, to do it. But, you know, there might be other ways. Anyways, I think that's it for this section. Parameterized surfaces, right? So it's just getting used to this idea of a parametric surface and what we can do with it, right? We can find the area of it, the surface area, that is, and we can find the tangent plane. Of course, if you want a tangent plane, you have your normal vector here. Right? So this is just n. This is just a normal vector n. So pointing outward from the torus. Right? Well, you know, here it's pointing outward this way, right? It can even be pointing inward this way, right? And just, revolve this around the z-axis, right? Right. They're not unit vectors, right? N does not have to be a unit vector. In fact, we know that because, you know, this is not 1, so the magnitude is not necessarily 1. In fact, the magnitude will depend on v here, right? So you have to be careful of that. So n will generally be, right, will depend on u and v. In this case, it doesn't depend on u, but it does depend on v. So the magnitudes of these vectors will vary, of course. Let me see. When v is 0, you get the maximum magnitude, I think. So pointing out this way, and then as you go up, it's less, right? So something like that. Yeah. All right, so yeah, and if you want the equation of the tangent plane, you do the usual equation like we did with the sphere. Okay, but yeah, torus, this is something we haven't probably seen before. This is a new surface, and again, it's, you know, as a challenge, you can try to write it in rectangular coordinates rather than the u and v coordinates here, but that would be quite a challenge. You know, you're welcome to attempt that if you want. So yeah, but we don't need that here. The more useful to have the parameterization rather than the equation with x, y, and z. All right, so that's it.